Okay, I'll give you the last part of this chapter. Give you the theorem like this. Which is called closed graph theorem. Closed graph theorem. And then we suppose that E and B, E and F, two Banach spaces. Two Banach spaces like this, and T a linear map from E from E to F. Linear map from E to F, and the theorem says that when the graph of J of T denoted by the graph of T like this, when the graph of T is closed, then T is continuous. Okay, very simple. The closed graph theorem says that when you have a linear map, two Banach spaces, and you have T is linear from E to F like this. If the graph is closed, then T is continuous. The graph of T denotes. I remind you that the graph of T it is contained the element like this for x or y, which E of F, such that y is Tx is on. They contain the limit like this for. Okay, what is that? E like this x Tx for all x being not E. Which is the graph of T. If this one is closed, then necessarily the T is continuous. Letter prove it. You need some lemma to prove it. For the proof, you need the fact that when you have E like this, a norm vector space with this kind of norm 1 and the norm 2 like this, such that the two, this one are Banach, this one for the one, and the norm of E for the second also are Banach spaces. If this one are Banach spaces, and this one, and if there exists a C, such that the norm 2 must be less than C, the norm like this, and one, then necessarily the two norms are equivalent. Then the norm 1 and the norm 2 are equivalent. That's what I thought. So if you want, I can read it, I can write it here clearly for you. You have a norm vector space with this two norms, this one and two norms on E. Say that E with this one is a Banach space, E with the norm 2 is also a Banach space. But then if there exists C such that you have this condition, then the two norms are equivalent. Then the norm 1 and the norm this one are equivalent. That's what. If there exists C like this one, that means that equivalent, that means that there exists another one, there exists C or B. C or B, which is like this, such that the norm of this one less than C, or B, the norm of 2 of x. That's not. So we have to prove this condition. That means that you have this one. In this case, since you have this condition, necessarily the norm are equivalent. So I will use this lemma to prove our closed graph theorem. For the proof of the graph theorem, for the proof, you have to prove also, you suppose that, let's assume that this one is closed. That J T here is closed. Is closed. Okay, this one is closed. Now then you have to prove that T is continuous. This one. You know already that F on A, F this one is the Banach space. And G of T is a close with this kind of norm, with the norm on this is close, this one is a closed subset of T, is a closed subspace of E, this one. Then necessarily G of T is also a Banach space. Is a Banach spaces. Okay, that is the first result. You can use after. Any closed subset of Banach space is a Banach space. We can now put the norm, this kind of norm of on T for all x in E. You can put the norm 1 of this x like this, which is equal to the norm of x in E plus the norm of Tx in Fx. And I put another norm, norm 2, which is equal to the norm of x like this. These two are the norm of this one. These two are the norm of your closed subset, this one. And then if you want to prove that T is continuous, what will I say? I would like to prove first of all that using this fact, that means that the norm 2, the norm here, the norm 2 is less than the norm 1. The version for this one is less than the norm 1. Oh, sorry. Okay, this is also. Then you have also. Then if you use the lemma, then the resistance C such that also the norm of this one must be less than C, the norm of the resistance is so. And this one implies that you have this condition T, the norm of Tx of F is less than some B, the norm of C of this one. The norm for B, the norm of this, then T is continuous. You just put it in it, this one, if you suppose you have this condition, you put it this one is less than this, then you have this one must be less than this kind of function. You have this one, the resist B, which is necessarily will be equal to C minus 1, something like that. C minus 1, B must be equal to C minus 1, such that the sigmatic is continuous. Okay, that's the proof of the closed graph theorem. The convex in itself is obviously it's obviously true. That means that if T is continuous, the graph is also closed. This one is very simple to prove. So I'll give you a remark for the last, that's the last remark concerning the BDL of this kind of space. Just a remark. Which does not concern, that's the last part that we say you study concerning the Banach spaces. You see that E is a Banach species. E is a Banach species, and I take the B dual. The B dual of E is like this. The dual of the dual of the dual. We can represent by the dual like this. It's the dual of the, call it the B dual of E, this one. And when you define a map from E into the B dual of this one, for all x you have this map E of x will be a map for the dual of E into R. So that if you have the map here, you have this one, dx of f, if exactly f of x is going to be defined as this kind. And when I compute the norm of dx like this, will be the norm of ds like this. It will know the supremorph of dx of f, the norm of this one, where the dual with the unipole of this one, which is exactly the supremorph of f of x when you have f like this, less than 1, which is less than from here, which is less than, you have this one, is exactly the norm of x. So we have proved that the norm of then the norm of x is 1, it must be equal to the norm of x's. That means that D is an isometry. Is an isometry, injective isometry. Then G is isometry. Then into the entity. Now, I want to tell you that if your E is not finite dimensional, your isometry is not necessarily a bijective. Once you know that an isometry just is a map which concerns the norm like this. Here you have the norm. Here, when I see the norm of this is not the norm of this. Here you are in E, here you are in the norm, it's the element of the norm of this kind of function. The B dual, the norm on the B dual of this one. Then it's an isometry injective, but not necessarily subjective. When you study the reflexive functional space, you study the case where it's subjective. Okay, so that's enough. So just you need it after. Okay, thanks.